Okay, it's a cylinder, radius of 0.2. So this is the radius. Standard atmospheric pressure outside. What's the smallest? Okay, what's the smallest wall thickness so that the maximum shear strain stays below this? Okay, so we know that so I guess I'm going to, maybe I'll sort of go through it a little bit, thinking it through, and then I'll show you sort of the quickest way we could go through it. I think it is helpful to think all the way through it, but I wouldn't hold you to that on a test. Although I was saying recently that I'm not going to, since it's so easy to derive, I'm not going to give you the formulas for these principal stresses. So you either have to remember those confidently or remember, I think the best way is just remember kind of a quick and dirty way to do that calculation. That'll stick with you more. But okay, so say we're looking at this point here. Okay, we have a stress, a normal stress along that, a normal stress along that. And those two are both tangent to the surface. And then we have the outward facing normal. And the way this works is, so for the X normal stress, let's say we isolate this piece. So we have the material pulling like this, the fluid pushing because it's a pressure, the pulling force from the material depends on the area of that ring. So we have the XX normal stress times the area of that ring, which use the trick where you disconnect the ring, straighten it out. So it's going to be the circumference times the thickness. So this is 2 pi r thickness.
Like if you were to rotate that face on.
Yeah, exactly. Yep. So like what's the area of that ring? So if it's finite thickness, then it's complicated. Well, really the way to do it is calculate the outer area and subtract the inner area. But if it's an infinitesimal thickness, you can disconnect the two ends and straighten it out into a long skinny rectangle. And we're assuming thin walls, so we're going to make that assumption here. Okay. And so this is equal to now the pressure times the area of the fluid on the inside, which is pi r squared. And now you can cancel a bunch of stuff. The pi's, you can cancel 1r, and you get that sigma xx is equal to pr over 2t. Okay. And now let's do sigma yy. So this one, we're going to be looking at a length L of this. I just like to draw this to show how awesome I am at drawing 3D shapes. It's like part of a Subway sandwich. And the material is pulling like this. The pressure is, the fluid is pushing like this. And setting those forces equal, you have sigma yy times the area of those two rectangles. The area of one of those rectangles is the wall thickness times L, and there's two of them, so this is 2LT. The area of that rectangle of fluid is, so this is the pressure times the area of that rectangle of fluid. That is the diameter of the cylinder times the length, and the diameter is 2R. So 2R L. Cancel the 2's, cancel the L's, and you get that sigma y is equal to P R over T. Okay, so the principal stress tensor then is PR over 2T, 0, 0, 0 PR over T, 0, 0, 0, 0. And that says then that the max shear stress is PR over T, the max principal stress, minus 0, the min principal stress, divided by 2. So that's PR over 2T. Okay? And then the strain, well, remember the Voigt strain is equal to the compliance times the Voigt stress. And so that is, so we have 1 over E, negative nu over E, negative nu over E, 0, 0, 0. And then I'm going to skip ahead, okay, to the shear elements, okay? And the shear elements, we got 0, 0, 0, 2 times 1 plus nu over E, 0, 0. 2 plus 1 plus nu over E, 0, dot, dot, dot. Okay. And I'm writing all of this just to say that an element of shear strain is equal to 2 times, just by the rules of matrix multiplication, 2 times the quantity 1 plus nu over E times a shear stress. Okay, so if we know that the max shear stress is this, we know that the max shear strain is 2 times 1 plus nu over E times PR over T. 2T, sorry. And those 2's cancel. So we just have 1 plus nu times PR over ET.
So you're just multiplying that, that max stress by the corresponding.
Right. Yep. And so You really could have skipped all this stuff if you just remembered this formula here. Okay? And then it's just a matter of going from the max shear stress to the max shear strain. But now you can plug this in as 1 times 10 to the minus 5 is equal to, it doesn't give a material. So let's just,
Always use 200.
yeah, you can use, yeah, that's fine. Or you can leave it in as parameters, you know. But, so yeah, so we got 1.3 over 200 E9 if it's steel times the pressure. Remember, pressure P is equal to the inner minus the outer. So that's about 3.9 times 10 to the 6. And it gives you the radius. And then you can finally, in the end, solve for that wall thickness. So 3.9 E6. The radius is 0.2 over T. Solve for T. Any questions about that one? Any questions about, I assigned you, I think, 2 problems, sort of simple internal loads problems. Any questions about those? Okay. So now back to internal loads. So last time, you know, so far we've done beams that are represented by just a single cut. Okay, so now I'm gonna go into multiple cuts, and I'm gonna do it with an example. So my example problem is we have this beam that's connected to the ground by a pin joint on the right end. And then we have a roller at the middle. And then we have 1,000 Newton force here and a couple twisting this beam of 200 Newton meters. And each half of this beam is 1 meter long. And we're neglecting the weight. When you include weights in internal loads calculations, you have to put them in as distributed loads. Remember that from statics, so we'll get to that next after this. And we want to calculate the internal loads as a function of x. As functions of x. Okay, so, well, let's first, before I start talking about it, let's just calculate the external loads here. So free body diagram of the whole thing. We have the 1,000 Newton force, 200 Newton meters. We have an upward force at the middle. I'll call that RA. And then we have an unknown force vector I'll call RB at the right. Okay. And I'm going to do, for this, since it's not internal loads yet, we're just doing the external loads, I'm going to calculate my moments around that point at the right end. Okay. So Newton's second law says 0, negative 1,000 plus 0 RA plus RBX RBY is equal to zeros. And then the moment equation about the z-axis says we have plus or minus a moment arm of 2, a force magnitude of 1,000. With the about point at the red dot, would that 1,000 make it rotate clockwise or counterclockwise? Counter, so that's a positive. Then we have plus or minus a moment arm of 1, a force of RA. Would that RA make it rotate clockwise or counterclockwise? Clockwise, so that's negative. And then nothing from RB, so this is 0. And so this tells us that RA is equal to 2,000. And then that tells us that RB vector is equal to 0 for x, and RB is negative 1,000. Any questions about that? All right, and then we still have to do the x one. So about x, we know we have the couple of negative 200. Which of these two joints is most likely going to counteract that 200? The roller probably is not going to, you know, it can probably just slide over that roller. So it's probably going to be the one on the right. So I'm going to, I guess I should have put it in here really. Let's do it like this. And I'm going to call this, I'm going to call this fancy TR for like reaction torque. And so plus TR is equal to 0. So since you've been off, you know, playing in the sun on your yacht, the one thing that we are doing differently now is we're including couples about the x-axis and these internal load calculations. It really doesn't change much. It just means that you have to always sum your moments about x in addition to what we're used to doing it about z. Okay, so this tells us that TR is equal to positive 200 Newton meters. And now we have our external loads. Okay, so now we have our external loads. I'm going to draw it out again. I'm going to just draw the whole thing with all this stuff we know. So we have a downward force of 1,000 here, a couple of 200 here. At the middle, we have an upward force of 2,000. And then we have a downward force of 1,000 and a couple of 200. So there's our complete free body. So now let's think about what our cuts are going to look like. Okay, I'm going to start out by, so I think it's always like reasonable. Anytime you get confused, remind yourself that you could do this if you had plenty of time. You could do this by just doing 100 finite cuts and never talking about X. You could just do it a centimeter at a time and go all the way, or in this case, 2 centimeters at a time, whatever. Go all the way across the beam and then just draw a curve through your values. Okay, so let's think about some finite cuts. So the first one is, let's do one where this distance is 0.0, let's just call it 1 centimeter, okay? So we have our 1,000 there, we have our couple of 200 there, and then we have our internal loads. So let me draw all the stuff that we're skipping. Okay, we're skipping the 2,000 here, the downward force, the 200 there. And now we have the loads that are applied to this little piece by the adjacent material. So that's a T, a V, a bending moment M, and an internal torque fancy T. Okay? And now let's think about another cut that is where the length is going to be 0.99 meters. And we're skipping all this. We're still skipping this force because we're not quite at it. And we're skipping these. Okay. But we do have the 1,000 here. We do have the 200 here. And we have all of the internal loads. Okay, and so the key point is these are qualitatively the same. They have the same loads on them. That's why we can represent these with a single free body diagram. Okay, and these are different by a lot lengthwise. They're almost a meter difference in length. Okay, but now I'm going to do one that's 2 centimeters longer than this, and it's going to be qualitatively different. Okay. Who has questions about what I'm doing here? Anybody, do you understand what I'm getting at here? What I'm showing is why we have to make the different cuts that we do. Okay, what happens to qualitatively, what happens to our free body diagrams to make us have to use a second cut?
Is this the same as what we were doing in static?
Yes, it is. Yep.
With the addition of the torque?
With the torque, yep, exactly. There's nothing new, right? I'm just trying to kind of, I think sometimes this can sort of, I think sometimes kind of centering yourself on the fact that, well, you could just always do 100 cuts and then just fill in the curves. It just takes a lot of time, So now now we're going to do this cut where this length is 1.01 meters. It's not much longer than that. And we're ignoring this material. We have the 200 over here, the 1,000 here. But now we've gone far enough that this force appears on our body. Okay? And that's why here we have to make a second cut. Our first cut can't represent this anymore. You know, here's our internal loads. So our first cut could have represented all of the first 99 cuts that we did, but now it couldn't represent this one because it doesn't show that 2,000 that would need to be there. Okay? And same thing, we can go all the way to this, where we're leaving off just this last little bit. This length is now 1.99 meters. And we still have the 200, the 1,000, the 2,000, and then the internal loads. And these are qualitatively the same. And so we could do these 100 different calculations, or we could just recognize we're going to do one cut that represents everything between these two, and we're going to do another cut that represents everything between these two. That's the idea of using X in these calculations. Okay. All right, so now I'm going to go in and do these cuts. So the first one is for all the X's between 0 and 1, non-inclusive of the endpoints. So basically, it's everything between this one and this one. And I'll just choose some representative picture.
And
Yeah.
also isn't very accurate on the very ends either.
It's, we're assuming that we can't calculate anything at the ends, and then we're just sort of filling in the curve. And so,
The curve will be pretty dang accurate for things that aren't on pressure points.
right, and that's a reasonable way to think about it, yep. Okay, so any other questions? Okay, so what do we have? We have the 1,000 here, the 200 here, and then the internal loads, T, V, M, and torque. And the length of this is X, where X is somewhere between 0 and 1, not including the endpoints. And so you get 0, negative 1,000, plus T. You know, you have a T0, you have a 0, negative V. I'm just going to put those in a single vector. Is equal to zeros. And so T is equal to 0, V is equal to negative 1,000. And then we'll go to the moment equation. I'll do Z first. My about point on the internal loads, on the cuts, is always going to be here. makes the math simpler. So we don't have any moment produced by the 1000. We have a couple m, and we have a minus Vx is equal to 0. So m is equal to Vx. Our V is negative 1000, so m is equal to negative 1000x. And then the moment equation about x, we have the external couple of negative 200 and the internal couple, fancy T, add up to 0. And so that internal couple, that internal torque is equal to 200 Newton meters. So for any x value between 0 and 1, these are the functions.
Is that pretty normal for twisting something where it's constant across the entire thing?
Yeah, because we won't have any distributed load torques. We'll never have anything other than that. It's hard to even really kind of imagine how that would come. Well, actually, I could imagine how it would come about. If you have a distributed load acting on, that's not acting along the centroid, then it's going to give you a distributed torque. But we won't have any problems like that.
Wrenches on a super long, like, octagonal rod, like one at the end and one at the halfway point.
Let's see.
Or would it be like twisting like a thin piece of steel or something like off center on the end of it?
It would be like, so with the wrench thing doesn't work. That would still be constant the whole way. But it would be like if you,
Really, well, that wouldn't be like, if you turn something from the middle, wouldn't it be like the other ones?
Or is it still?
Okay, so let's see.
Distributed?
So if we had, so let me first do the way I know it would work. So imagine if you have, imagine that you had like a long like shelf on this thing, you know? And then you had a distributed load acting on this shelf and it's offset, you know what I mean?
Mm-hmm.
Then this is going to be producing a variable internal torque as you go along. If you had, let's think of it as screwdrivers because I know how to draw those. So if you had one screwdriver here, okay, so, and one screwdriver here. That's what you were talking about, right?
No.
Oh.
Imagine that's like a hex bar, and there's a wrench on the middle of it.
Okay.
The right side is affixed to the wall.
Okay, right. Okay. Yes. So in that case, in that case, so you have your wrench like this, cranking on it, and you have, this is fixed to a wall, and maybe you have something else, another wrench that way.
Mm-hmm.
Then you'll have piecewise constant torques, one value up to here, one value after there. But what we won't see in any problems in this class is we won't see anywhere where you have a continuously varying torque about X. But with something like this, you could. But you'll never have to worry about that because I can't imagine trying to make that figure.
That's what finite elements are for.
Yeah.
Thank you.
Yeah. Okay, so so this was our cut that represented every possibility between these two. Now we're going to our second cut that represents every possibility between these two. Okay, so now our cut 2 is for x values from a little bit bigger than 1 to a little bit less than 2. And so I'll draw a representative piece. The length of this is x, but this time x has to be somewhere between 1 and 2. And we have the 1,000, the 200, the 2,000, and then T, V, M, and torque. And notice that that free body diagram looks exactly like this second pair that I did. Newton's second law says 0, negative 1,000 plus 0, 2,000 plus T, negative V is equal to zeros. So T is equal to 0 and V is equal to positive 1,000. And then the moment equation about the z-axis. Again, my about point is going to be here. So there's no moment there. There is a counterclockwise moment from the 2,000 with a moment arm of 1. So I guess I'll write this as it's counterclockwise, so it's positive. Moment arm is 1. Force is 2,000. Plus m minus Vx is equal to 0. So m is equal to Vx minus 2,000. And so that internal bending moment is equal to 1,000x minus 2,000. And then the moment equation about the x-axis, we have negative 200. Nothing else produces torques until you get to that internal torque. So plus T is equal to 0. And so T is equal to positive 200 Newton meters. Okay, so you always, generally speaking, in general, the internal loads are piecewise functions. Where do the subfunctions change? That's where you have to change cuts, is where those subfunctions change. They change at point forces, point couples, and places where the distributed load function changes. Okay? And remember that we haven't talked about this yet. I mean, even though I keep mentioning it, let's pretend I haven't talked about it yet. We're going to eventually always consider the fact that dm dx has to be equal to v, and dv dx, negative dv dx, has to be equal to the distributed load function. So those are checks you can always do. Let's check these on our on the distributed loads above. So on the second cut, dm dx is equal to 1,000. That's what v is, so that works out. Okay. V is a constant, so negative dv dx is 0, and we haven't had any distributed loads yet, so the distributed load function is 0, so that works out. If we go to the first cut, dm dx is equal to negative 1,000, so that's equal to v. Negative dv dx is 0. There's no distributed load function, so that works out. So now we're going to do distributed loads. And remember that the weight always has to be treated as a distributed load. I'm going to do a really simple one so that we can get something done before class is over. I'm going to do a cantilever beam. I'm going to make it 3 meters long. And I'm going to say the mass of this beam is 30 kilograms. Okay. Since I have a cantilever at the right end, that's never going to show up in our cuts, so I'm not even going to calculate the external loads to start with. I'm just going to get right into it. Okay. So let's think of a free body diagram of the whole thing. Over here, we have a reaction force. We also have a reaction couple, MR. But the weight is a uniform distributed load that's equal to, this mass means that mg is equal to 294.3. And so if you divide that by the length of the beam, you have a uniform distributed load with a magnitude of 294.3 divided by the length. Newtons per meter. And this comes out to be 98.1 newtons per meter. Okay, so we only need one cut for this one. So this is for x values all the way from 0 to 3. We have this distributed load of 98.1 newtons per meter. And we have the internal loads in this case, we don't have any torques about the x-axis, so you can just leave it off. Or you can put it in there and you'd calculate that it's 0. And so before we can do any calculations with this distributed load, we have to come up with the equipolant point force for this. So let's think about this rectangle. Our cut has a length of x. So this rectangle has a length of x and a height of 98.1. The x position of the centroid of this rectangle is right in the middle. So we know that this length is x over 2. And the area of this rectangle is just the height times the width. So 98.1 times x, or 98.1x. So now I'm going to redraw this free body diagram, given what we just figured out about the equipolant point force. At the center, the centroid of that rectangle, we have a downward force of 98.1x because that's the area of that rectangle. And then we have the internal loads, T, V, M. And now we can go to Newton's second law. It says 0, negative 98.1x plus T negative V is equal to zeros. So T is equal to 0 and V is equal to negative 98.1x. And then the moment equation about Z, we have plus or minus a moment arm of x over 2, because this distance is x over 2, because that's where the centroid of that rectangle was. Times a force of 98.1x plus m minus vx is equal to 0. So m is equal to vx. Oh, I didn't do the plus or minus. If our about point is over here, this downward force would make it rotate clockwise, so that's negative. Get it over on the other side, and that's positive 49.05 x squared. Plug in our v value, do the algebra, and you get m is equal to negative 49.05 x squared. dm dx is equal to v. This time we do have a distributed load function. Negative dv dx is equal to 98.1. And that is our distributed load function, a constant 98.1 acting down. Any questions about that one? Okay, I'm going to give you a couple of distributed load problems. Feel free to bring them on Monday, and I can go through any you want to see. Okay, have a good weekend.